Hello everyone. Today we are going to learn 7.1. So chapter 7. So we learn chapter everything before 7. So today we do continuous random variable. So what was the continuous? So it's a measurement, right? So it's about the decimal, right? So I wrote down this one. Measurement decimal. But then we have random variable, right? So we're using random because there is probability related, right? So the outcome, if the outcome of the experiment is measure, since measure is a continuous random variable, right? So random means the value of variable occurs by random chance. That's why we are using random, right? Okay. We have bell shape again, and then we have a learning objective here. Okay, 7.4, sorry, 7.1, we have learning objective. Sorry, that was not learning objective. That is a chapter outline. Learning objective for 7.1. Okay, so let us take a look this one, area and probability. Assume that you have created a square board with a side length 1 meter each. So this is one each. Well, I'm sorry, one each, 1 meter, and this is 1 meter. If a dart is thrown at the center of the board, it will randomly land somewhere on the dartboard, shown figure 7.1 here, yeah? So we want to find what is the probability it lands at the exact center here of the dark board, right? Okay, so the first one, we want to know about what's the probability the dart at the center, right? Okay, so that means how many dart at the center, right? And divided by number of sample sample size, right? Okay, so how many dart at the center? There's only one center, right? So only one over. And how many sample space is there? So we have uh, so many sample spaces there. Can you see that? Yeah. So we say that this is so many. What do you want to pick? A million? So 1 million. One million. Yeah. Can you please calculate? 1 divided by huge number, right? Okay, so we get the 0, yeah? So there is the probability is 0, which is similar. It's approximately make it 0, right? Or equal to 0. Yeah, it's impossible. It's very hard. Only the professional make the center. But luckily we get sometimes, right? Yeah. So we say that 1 million, but then there is infinitely many, right? So 1 over, we say that this symbol, infinitely many sample size, right? Infinite number, basically, right? So means infinitely many sample size there. Yeah, makes sense? Okay, so second one, what is the probability it lands in the shaded region? Let me bring nice picture. Oh, you cannot see. Let me bring nice picture. Okay, second part, what's the probability of a shaded region, right? So equal to number of shaded region divided by total number of sample space, right? Size. And we can say the SS, yeah? All right. So how many shaded region there? It's only one. And how many sample spaces there? It's a 4, right? Okay, what do you get this 1.25? Good. Now, the third one, what is the area of shaded region? Okay, once again, we can see the C from the B, right? What's the area? That's weird. Yeah, all of a sudden we want to find the area. We were talking about probability, right? All right. So what's the square? This looks like a square, right? So what's the area of a square? So we make length times width, right? Or side times side, because in the square, all side is the same, right? So equal to side times side. Then, since we have whole thing is 1, so we will get 1/2 each side, right? 1/2 here, 1/2 here, which is 1, right? And also 1/2 here, 1/2 here too, right? So we will get 1/2 times 1/2, which is 1/4, which is 0.25. What can we see? That's why they ask us the area, right? Look, we have a probability of a shaded region here. We get 0.25. If we want to know about the area, the shading part is 1/2 times 1/2, which is same as 0.25, right? So we can conclude area is the same as the probability. Make sense? All right. So, and also we can say the total area, which is 1 times 1 in that case, right? The area of shaded region represent probability. Hold on 1 second. Yeah, I see. So let me close this one and then what I just said, let's go back. So area is the probability, and then what I just said that when the total area of any region 1, the area of shaded region represent probability. So basically what I said, area is the probability. Make sense? Okay. Here we go. Area is a probability for continuous random variables. And we say that proportion also, and we say the percent. We can express, right? Yeah, area, probability, and proportion, and percent for continuous random variable. Okay, now we have probability density function, PDF. We are using first letter, right? So PDF. It's a function used to find probability. So total area under the graph of probability density function is 1. Then we can find the area shaded region, right? Okay, so area under the curve is 1. All right, so we have a uniform continuous, I'm sorry, uniform distribution, right? So when we hear uniform distribution, what we are thinking about, right? We did this one before, right? Uniform, right? So equally, everything equal, right? So in that case, equally likely, so random variable X has uniform distribution if all outcomes are equally likely. Yeah, that's so uniform. So we have distribution, same, right? Yeah, we had the same. Equal. So we have a graph here. So everything is the same. That's the uniform, right? Okay, now we have the example. So Bart is a commuter. And then Bart riders who transfer at the Millbrae station must wait between 9 to 16 minutes for their connecting train according to Bart's statistic. Due to scheduling, the wait time for connection follow uniform distribution graph. The probability density function for X, the wait time for the connecting train. Okay, let us do this. All right, so how to graph? 9 to 16 minutes, right? So 9 from here, approximately, and 16 over here, approximately. All right, so we have a rectangle. Shading reason. All right, X is between 9 to 16. So that will be 16, 16 minus, excuse me, 16 minus 9, we have a 7, right? So 7. All right, then what's the area of rectangle? So we have A equal to L times the length times width, right? Or we can say the length times the height. All right, so we need that. Let me make here. A equal to length times the height. Let's denote it this way. Then area, we know 1. The total area, we knew the one, right? The earlier we did that, the probability of density function, the under the curve, total area is the one, right? 1 equal to, then length we have 7. Then what's the h will be then, right? So this will be h. Make sense? Okay, then we divide by 7 both sides. Different color. So h equal to 1 over 7 there, right? So it will be 1 over 7. Yeah. And that's the graph. They say the graph, right? Yeah. All right. All right. So use the uniform distribution from example 2 to find the first one. What is the probability that commuter will wait between 9 to 12? So between 9 to 12, between 9 and 12, right? Okay, so we know that area equal to length times the height. So 12 minus 9, yeah, from 9 to 12. Oh, this is what we did earlier, right? It's 7, right? I'm sorry, 12, no. It was the 7, it was. This one is a 3. Then height is 1 over 7, right? Yeah, we had that. So that will be 1 over 7, which is 3 times 1 over 7, which is 0.4286. Good. All right. Second one, between, oh no, not between, more than 10. More than 10. Okay, so I have to mention that that is a probability, right? So this is a probability. Probability x between 9 and 12. More than 10. We can express a probability more than 10. No equal sign. Okay. Then the area, which is length times the height. So more than 10. So 10 to the 16. So 16 minus 10, right? And the height will be 1 over 7. So that will be 6 times 1 over 7. What do you get? 0.8571. Yeah. Okay. So previously we had a discrete random variable. We have a binomial random variable, right? So when we use inequality, so binomial also we are using discrete number, right? So the equal sign very important previous one, discrete number, right? But then in that case, it's a continuous number. So it does not matter 10.1, 10, 10.00001. They are very similar, right? So they really don't care. Equal sign, not equal sign. Make sense to you? Okay, let me write down then. All right, so here we go. And see, what is the probability that uh, a commuter will wait longer than 15 minutes? So longer than 15. So we're using the probability is greater than 15, right? Longer. And then area will be length times the height. So we have until 16. So 16 minus 15 times 1 over 7, right? Then 1 times 1 over 7, which is 1 over 7, which is 0.1429. All right. So let's do the last one between 10 to 15 minutes. Yeah, 15, yeah, between 9 to 12, 10 to 15, right? So the between how much? 10 to 15? 15. So we can use that. Um, 10, 15. Yeah. So continuous number, you really don't have to have an equal sign. So area equal to length times the height. So length 15 minus 10 times height 1 over 7, which is 5 times 1 over 7, right? So we get 0.7143. So that's the probability waiting time between 10 and 15 minutes, right? All right, very good. Okay, so I'm gonna show you how to use a StatCrunch. So I'm gonna show you from previous example, the ABC. Okay, so we have normal curve here. So this is a bell shape, and we are using normal curve in this chapter because we are dealing with a continuous number. So we can say the normal curve is a bell shape, but then all bell shape is not normal curve, right? Because some bell shape deal with discrete number, right? Okay, so we have a normal curve. This is the green one, standard deviation one, and blue, normal curve with a standard deviation 1.5, and normal curve, this is red, the standard deviation equal to 2. All right, so we have properties of a normal curve, normal distribution. So they are unimodal, yeah, because only one peak there, and symmetric about the mean. So this is a mean, and then left side the same as right side, that is a symmetric means, right? And horizontal axis is a horizontal asymptote, means that the curve getting close to the horizontal line but never touches. Yeah, means the curve never touches the horizontal line. Let me denote it like that. Too long, right? Horizontal line. All right. One standard deviation above the mean, one standard deviation below the mean, or inflection point. So inflection point, this is the inflection point. Oh, It's a it's hard to explain because of this calculus stuff, right? So like this, right? So we called this is a hold water. This is we spilled water. So inflection point, we say that uh, that is concavity change, right? So concavity change. Then what is the concavity? Change when concavity change. So we say that hold water concave up. That's a mathematical terminology, concave up. This is concave down. So in the case, can you see that? This is hold water in this part, right? And then after this part is spilled water. Can you see? Holds water, this part, and spills water there. Yeah. So that point is concavity change. Same as here, holds water and spill the water, right? So at this point, the concavity change up and down, down up, right? So we call this is inflection point. All right. And then the total area under the curve is the 1. Very important, right? And then the function curve, the formula is this, but we're not gonna use this one. Too crazy, right? So we're gonna use this secant. And then empirical rule, we're using in that case, so same, right? Bell shape. So 60, 80% within one standard deviation from the mean, 95% using for 2 standard deviation from the mean, and 99.7% using for 3 standard deviation. Yeah. Okay, so let us do this example. So we have the cell phone every 2.8 years on average. I just omit this sentence. Let X be the replaced time or lifespan of cell phone. And the mean is 2.8 and standard deviation for replacement is 1.1 years. We want to draw the normal curve. Yeah. So mu equal to 2.8 in that case, right? Okay, so inflection point here, so we know that that is mu plus sigma. So mu in the case 2.8 plus sigma, which is 1.1. Can you please calculate? It's 3.9. Okay, how about the other side? Mu minus sigma, so 2.8 minus 1.1. So what do you have? 1.7. Okay, good. Now, the next one is, it's about here, right? So there will be mu plus 2 times of sigma. So there is mu minus 2 times of sigma. And the next one is, it's hard to see. So mu plus 3 times of sigma. And here is mu minus mu minus 3 times of sigma, right? So there is no space, so let us do that here. How about mu minus 2 times of sigma first? So mu, which is 2.8 minus 2 times of sigma, which is 1.1. Can you please calculate? 0.6. How about mu plus 2 times over sigma, 2.8 plus 2 times 1.1, 5.0, good. How about mu minus 3 times over sigma, so 2.8 minus 3 times over 1.1. Can you please calculate? So negative 0.5. How about mu plus 3 times over sigma, 2.8 plus 3 times 1.1. So we get, what do you get? 6.1. Okay, so here is mu plus 2 times over sigma, 5.0 there. Here is 6.1 there. Here is a 5.0 there, and then here is a 6.1. Yeah. No, negative 6 point, negative 0.5. Yeah. And sorry, negative 0.6 then, 0.6. Yeah. 0.6. Copy wrong. Yeah. So there's a negative 0.5, 0.6, 1.7, and 2.8, 3.9, 5.0, 6.1, right? All right. Okay. All right. So we have this example. Find the mean and standard deviation, right? So we knew this is the mean, right? So 48. Mean equal to 48. What about the standard deviation? So we knew this is mu plus sigma, right? So that will be 55 equal to mu equal to 48 plus sigma. Then we need to solve for sigma, right? So we subtract both sides of 48. Then what do you get? 7. Yeah. Can you check? Check it out. Check the answer. So sigma equal to 7. We have a 41. Check the answer. Check the answer. So 41 equal to mu minus sigma, right? So there will be 41 equal to mu, 48 minus sigma, right? Is it same? Check that. Yes, it's the same, right? So 41 equal to 41. Excellent. Okay, how about this question? So many say unknown, and we have two part. It's a given. How do you find middle number here, right? So it's a middle number, how? So like average, we need to find the average, right? From the two numbers, so mu in the case, 13 plus 21 over 2. Can you calculate? It's 17. Very good. So now we knew this number mu plus sigma, right? Okay, so there will be 21 equal to mu plus sigma. Then mu equal to 17 plus sigma. Solve for sigma. So subtract 17 both sides. We have 21 minus 17, which is a 4, right? So 4 equal to sigma, right? Okay, let's check that here. Okay, so we have a 13. So 13 is mu minus a sigma. So 13 equal to mu minus a sigma. So 13 is the same as mu, which is 17 minus 4. Yes, right? Yes. Very good. Okay, looking at this question, this is what we did earlier, and then we found every numbers here, right? Okay, the first one by empirical rule, estimate the probability cell phone between 1.7 and 3.9. This is a 68%, so probability is 0.68. Probabilities between 1.7 to 3.9, 0.68. What about the between 2.8 to 5.0? Yeah. This one I went over in the beginning when I introduced empirical rule, right? So 68% divided by 2, what do you get? So 34% each one, right? So 34%, 34%. And then 95% and 68% occupied, right? So there will be 95% subtract 68%. So 95 minus 68 is 27%, so 27%. But since we have two portions there, so each one has 13.5%, right? So let me write down. 27% divided by 2 is a 13.5% and 13.5%. Yeah. Okay. So 2.825. So we will get the 34 plus the 13.5, right? So probability was between 2.8 and 5.0. Ooh, why is a little bit weird. So this 34. Let me just using percent first and then convert to the decimal later. 13.5%. So that will be for 47.5%, which is 0.475. Yeah. Okay. All right. Now, the third one, the last longer than 5 years. Longer than 5 years. So from here to here, right? So we knew 99.7%. 99.7% minus 95% is occupied, right? So we have how much? Calculate. 99.7% minus 95%. It's a 4.7%, right? Yeah, that's it, right? So oh yeah, but then we have to divide by 2 because the 2 portion there. So 4.7% divided by 2. Okay, but then what happened to last one? Last one has 100% minus 99.7%. So that will be 0.3%, right? But then we have two portions, so 0.3% divided by 2, we get the 0.15%, right? 0.15% each side. Yeah. So so there will be 0.15%. So the last one longer than 5. So x is greater than 5. That will be 2.35% plus 0.15%, right? That's 2.5%, isn't it? Yeah. So that will be 2.5%. 1, 2. So that will be 0.025, right? So we make a 1, 2. Beyonce method, right? So same method. So we're using from what is called percent to the decimal, right? Convert percent to the decimal. So we make to the left twice. So in that case, we have 2.5, 47.5%. So 1, 2. So it's a 0.475. We have 2.5%. 1, 2. So we have 0.025%, right? I'm sorry, 0.025, right? All right. Done. Thank you for watching. I will see you next time. Bye.